All right, we're now getting into our geometry portion of math studies. So we're now in chapter 16. So here's the first lesson on this one. In the first lesson, we're just kind of looking at right triangles and just doing a couple reminders, some things that we know about right triangles. So in these first few examples, working with special right triangles, the special right triangles fit one of two patterns. They are either a 45-45-90 or a 30-60-90. So those are the two pattern of angles that we find as special simply because they create special ratios within the side lengths that we see for the triangle. So the reminder for a 45-45-90 is that the two legs are the same. So these are your base angles, and that makes the two legs equal because the base angles are equal. So we're going to call this guy X and this guy X. And if you know your two legs in a 45-45-90, we can always get the hypotenuse by taking one of those legs and multiplying it by the square root of 2. So this is the pattern for a 45-45-90. If you take out the x's, then the other way of looking at this pattern is a 1-1 rad 2 pattern. So we can either do it with variables or without variables. So if you look at the blue, that's one way of looking at it as x, x, x rad 2. But if you eliminate the x's, then we can also look at it as a 1-1 rad 2 ratio for those guys. So if you ever know a leg and you're trying to get to the hypotenuse, you just multiply by the square root of 2. If you ever know the hypotenuse and you're trying to figure out a leg, you just divide by the square root of 2. And so we're just going with one of those two operations within that kind of a triangle. If you look at your 30-60-90, 30-60-90s, with the short leg is always across from your smallest angle, which is 30 degrees. Your long leg is always across from the 60-degree angle. And the ratio from short leg to long leg is that we multiply by the square root of 3. And so that's how we get from short leg to long leg. If you know your long leg and you want to go this direction, then we divide by the square root of 3. From the short leg to the hypotenuse is always across from the right angle. But from short leg to hypotenuse, we just double the short leg. So we multiply by 2. So that means that if you wanted to go from hypotenuse to short leg, you just divide by 2. Notice that we never go back and forth between long leg and hypotenuse. We never go that direction. So everything goes through the short leg, which is this guy. So again, if you wanted to leave out the x's and just throw in a number pattern, then we are looking at a 1-2 rad 3 ratio between those three segments. All right, so just to do a couple quick examples, right here, if we, in a 45-45-90, just based on what we talked about right here, if I know that the hypotenuse is 8, and I want to figure out either leg, then I just need to take my hypotenuse, divide it by the square root of 2, and that's going to give me one of my legs. And we know that the legs are equal, so once I find one, I know the other. But if I were to take 8 and divide that by the square root of 2, always do clean up wherever possible. So one of the things that we always stick with is we tend not to leave a radical in the denominator. So if I multiply the top and the bottom by the square root of 2, then I get 8 rad 2 over 2. So it's going to look like this, and then again, now I can do one more step of cleanup because I'm allowed to do 8 divided by 2 and get 4. So 4 rad 2 is going to be the value for both legs. So A and B would both be 4 radical 2. Over here at the 30-60-90, again, just kind of going off the numbers that we talked about right here. If I know the hypotenuse and I'm trying to get to the short leg, then I just divide by 2. So if this is 8, then my short leg is 4. And whenever you want to go from short leg to long leg, we just multiply by the square root of 3. So this becomes 4 rad 3. And that's it. So when it comes time to knowing these, most of this could be done without the knowledge of these special right triangle patterns, sometimes Pythagorean theorem is enough. A little a squared plus b squared equals c squared. Sometimes that would be enough. These rules just tend to be shortcuts. So it's like if you know them, then there are some nice shortcuts available for you. But if you don't recognize the shortcuts, then oftentimes either Pythagorean theorem or SOHCAHTOA would work instead. So moving on down to the next part of this, which is SOHCAHTOA. SOHCAHTOA is used when you don't have special right triangles. So if I see 40 degrees or something like this that doesn't fit one of those special right triangle patterns, well, then I need another method, and that's where SOHCAHTOA comes into play. So just a reminder on your SOHCAHTOA acronym here for what that means. Whenever you're looking at a right triangle like this, from any angle, from any acute angle, right, the leg across from that we consider to be the opposite leg. The leg that is next to your angle is the adjacent leg. And then the hypotenuse is always the hypotenuse, no matter what angle you're working with. So based on that, we know that the sine of an angle is equal to the opposite leg over the hypotenuse. We know that the cosine of any angle is equal to the adjacent leg over the hypotenuse. And we know that the tangent of any angle is equal to the opposite leg over the adjacent leg. So I know you all have seen that before. Heavy dose of that in geometry. Definitely some of that would come up within math analysis as well. This is a big portion of trig right here. So, and I know a lot of that's being now filtered into Algebra 2 also. So I know we've seen this in the past. So here's just a few examples. We tend to want to work with the angle that we are given. So I know this is 40. Do keep in mind that if you know this was 40, well, what would that make this angle? We know this would be 50 degrees, simply because if that's 90, right, then these two guys have to make up the other 90 degrees within this triangle, right, because we know all triangles add up to 180. So if that's 40, this must be 50. So even though I know this is 50, I still like to work with what they give me and not what I come up with. It's just a safer approach. You might make a careless error, and so I like to play it safe and just use what they give me. So in this case, let's just start by solving for y. It doesn't matter which you want to start with. Let's just pick y and go with that. So from this angle, if this is the angle I want to work with, then this becomes the opposite leg, and from here, this becomes the adjacent leg. So based on our key right here, we know that tangent is the one that works with the opposite leg and the adjacent leg, so that's going to be our setup. So we're going to say tangent of 40. So you always get your trig ratio with the angle on one side of the equation. The other side of the equation are the segments. So opposite leg over adjacent leg. So opposite over adjacent, 6 over y. And so all I have to do now is solve that equation for y. So to get y by itself, we would multiply y over to here and then divide tan 40 over to here. And so if you get y by itself, your setup is going to look like this. 6 divided by tan 40. And that's what's going to go into our calculator. Of course, we want to make sure our calculator is in degrees when you do this. So do check. The default mode of a calculator is radians. So if you ever change your batteries or reset your calculator or do something like that, you do need to make sure your calculator goes back into degrees. So I'm going to hit mode, go down to this guy, switch over to degrees, and just hit quit. And so now I'm in the right mode. So now I can do 6 divided by tangent of 40. And 3 sig figs as always. So 7.15 is my side length for y. And if I want to do the same thing in solving for x, again, from this angle, x is always the hypotenuse. In this case, this is the hypotenuse. But from this angle, we know 6 is the opposite leg. We know x is the hypotenuse. And so if I look up here, I can see that sine is the one that deals with the opposite leg and the hypotenuse. So we're going to say sine 40 So remember, with any trig ratio, it's always connected to an angle. And then the other side of the equation, we put the segments. So opposite over hypotenuse, 6 over x in this case. And then again, if I want to solve for x, I would multiply the x over to here, and then divide sine 40 over to here. And so we're going to say x is equal to 6 over sine 40. And that's what goes in the calculator. So again, making sure we're in degrees, so I'm going to do 6 over sine 40, and 9.33 to 3 sig figs. Just a quick check, one thing you should always know about any triangle is that the shortest leg is always, or the shortest side is always across from the smallest angle. The largest side is always across from the largest angle. And then, of course, the middle angle would be across from the middle side leg length. So you can always check that ratio and make sure the numbers work out that way. Looking at this guy over here, the difference on part B is we know the side lengths, but we don't know the angle. One thing, just as a quick side note, if you did want to find the missing piece of our triangle right here, a little Pythagorean theorem would do the trick. So this is a little 5 squared plus 12 squared equals c squared, which if you were to solve that, you would come out with 13 as your hypotenuse. If I'm looking for this angle, we'll call it theta. So I'm looking for angle theta. Well, from this angle, 5 is the opposite leg, and 12 is the adjacent leg, and 13 is the hypotenuse. So those are the three things that we know. Again, I don't like to use my numbers. I like to use what was given to me just in case I made a mistake. And so I'm going to work with these two guys. And so from here, I know that tangent is the one that works with the opposite leg and the adjacent leg. And so we're going to say tangent of theta. That is now our unknown. Remember, trig ratios always go with an angle, and the side legs go on the other side. Well, how do we solve for a missing angle? We simply take the inverse function, so the inverse tangent of 5 over 12 is going to allow us to solve for theta. So if we go into our calculator right here, and right above tangent, let me do this. So right above tangent, we see the inverse tangent. So I'm going to hit second tangent of 5 divided by 12. And about 22.6 degrees is theta. Remember, the rule is 3 sig figs unless the directions say otherwise. And you will get directions that say otherwise. They might say to the nearest whole number, right? And so we would have used 23 degrees instead of what we have. So just read the directions. But if the directions don't say, then always go with 3 sig figs. From here, just as a side note, if you did want to find your other angle, the other acute angle, just like we talked about over here, because this is 90, then these guys are the other 90 degrees of this triangle. So if I did 90 minus 22.6, then I'm going to get that angle right there. One last case. In dealing with this notation, this is something called minutes. Minutes and seconds is kind of what you're seeing on this. This is not a common IB notation. It's just something used within our book. So I introduce it just so that you know what this is when you're doing stuff. When you see this in our book, even though we're not going to be tested on this format, I just want you to know what it is in case we see this in our textbook. So when you see this, this is instead of doing decimals. When you do a decimal like this, we always know that decimals are out of 100. So if I see 0.33, I know that's 33 out of 100. But when I see this in terms of minutes, well, if you think of minutes for a minute, no pun intended there. When you think of minutes, minutes are out of 60 because it takes 60 minutes to make an hour. So the way that we would interpret this is 39 degrees and 17 out of 60 minutes. So that's what we're getting out of this. So if we wanted to convert this in our calculator, we're just going to do 17 divided by 60 to get the decimal that's going to follow the 39 here. So it is essentially in your calculator, it's 39 plus 17 out of 60. So if I did that in here, then 39 plus 17 out of 60 would allow me, to convert that into a decimal. So that's the decimal that we're working with here. If you were to solve for y, in this case, let me just finish this one off. Again, based on our SOHCAHTOA acronym that we see up above, we know that y is the hypotenuse. From here, this is the opposite leg. And so if I wanted to solve for y, I know that sine is the one that deals with the opposite leg and the hypotenuse. So we're going to say something like the sine of 39 and 17 out of 60 is equal to opposite over hypotenuse. And again, if I wanted to solve for y, I'm going to multiply the y over to here. I'm going to divide the sine function over to here. So in my calculator, I would be doing 16.3 divided by the sine of 39 and 17 out of 60. So that's what's going into my calculator right now. So I'm going to do 16.3. And I'm going to divide that by the sine of this answer. Since that was my last answer, I could just pull up my last answer if I wanted to plug it in that way. Whatever you do, don't round it. We always want exact measures. We try not to round until the end of the problem. So I could even do this and type it in that way if I want, just for accuracy's sake. So about 25.7 degrees, or sorry, 25.7 units is side y. So that's what we're looking at here. Oftentimes you're going to run into directions that say solve the triangle. Whenever they say that, that just means find everything that's missing. So in this case, I now know that this is 25.7. I could use another trig function to find this guy if I wanted to. Also, if I subtract this from 90, I get my other angle. So, all right, those are always tools that we have for finding anything that's missing on these guys.